So here's a basic example of MIPS, or programming in general. So to express this in MIPS, this is a high level. So you have two variables, A, and then you're assigning to B plus C. So as you're familiar with assembly language, this is the MIPS syntax for that. You add, and then you specify the destination register, and then the two source registers, which are B and C. So instead of using A, B, and C, we're using specific registers that are that MIPS recognizes, and this would be the final syntax for that. So this is a lot, but just know this is what how the program would be implemented in C for my sample project. So you have an array of certain values, so that would be stored into the RAM, and then you just have your program, and this is a very high-level description of that. In your own time, you can go ahead and review this more in depth. But this is how it was written in assembly. You don't have to understand all of this now. You can revisit this at the end of the presentation. So as mentioned previously, you have registers that MIPS works with. There are a total of 32 registers. Register 0 has a constant 0 to it, so you can use that. And the benefit of that is you just have easy access to the value 0, which can be useful in many different applications. And all these registers are free for you to use, despite the usages. So if you wanted to, you could use A0 for something other than its intended purposes. And it's generally just convention to use these specific registers for those specific purposes. So when other programs are using it, they have an idea of why you're using that register. So you want to add to it?
Not this one.
And then if you're interested in implementing functions, the last 4 registers might be something of interest. We won't be discussing how to write functions, but we have linked a PDF for you to go ahead and play around with and read. If any of you wanted assistance on that, you can ask us individually.
So one thing I wanted to highlight is the relationship between the registers, the instructions, and the memory. Just to give you a context of what you're doing when you're manipulating assembly is you're interacting with these devices, right? So as we just talked about, we had the register file, and the register file interacts with the execution unit, which is performing all of your calculations, the add, subtract, the logic operations as well. That's happening in the execution unit. And then on the other side of this is the instruction memory, where all of your instructions come from. The program counter is responsible for selecting these instructions. And I think you guys might have discussed this in 127, possibly. This program counter is important also for if you want to do function calls and manipulate the program counter so that you then select the function that you are working on and then jumping back to where the execution was before. And then we have next is the data memory, which is where, for example, your arrays will reside. And finally, the control unit, which drives the components in order to execute those instructions. Right? And so that's really what we're talking about when we're talking about the MIPS processor is the program counter, the register file, control unit, and the execution unit. Those are the basic components that reside inside this processor. And then this processor is interacting with the memory devices. And so that's the relationship to the system design is, again, we have the MIPS processor, the instruction memory, and the data memory. And the way that they're tied together is just like how we talked about before. Okay.
So MIPS assembly, there's three types of instructions. You have an R-type instruction, which only deals with register-to-register operations. You have I-type, which uses a register and an immediate operand, so you can specify a constant. And you have J-type for program controls to do jumps. And then there's a MIPS green sheet reference card that you can visit. And it details all the instructions that are supported, as well as the syntax and for them. So a little more in depth. R-type. So in the top right-hand corner will be the syntax for MIPS on how to write this operation, and then there's going to be some examples on how to use them. So for an R-type, you have three fields. You have the RS, RT, and RD. RD is the destination, and as mentioned, it just uses registers for the certain executions. So. And then I-type is with immediate values. It's usually appended with an I. And usually R-type values have a corresponding I-type operation. And you have two types, arithmetic and logic. And due to the immediate value only being 16 bits, it needs to be extended. So for arithmetic operations, it extends the most significant bit. So it preserves the negative and positive values. And for logic, it just zero extends it. You don't really need to know much about that, but just review the MIPS screen sheet to know which types of operations you can do. And then load word and store word are used to interface with peripheral outside of the MIPS processor, and they cause a bus cycle. There's a signal on the MIPS processor that indicates whether it's a bus cycle or not. And to write to a memory location, you have a base, which is specified in the parentheses, and that is added with your offset, which is the constant value that you write before the parentheses. So in this case of load word, it's going to take whatever value is stored in T0 and add it by 40, and then reference that memory location. And that address will be outputted onto the address bus, and then you can go ahead and read them. Same thing for store word, which writes to the external memory. Another I-type is branch equal. This is especially useful in you doing conditional operations. So it checks two registers to see if they're equal or not. If they are equal, it'll go ahead and jump to your specified label, in this case loop.
Yeah, the call online is dropped, so this is the entire time.
Oh. Okay. It is. Finally, you have the J-type, which jumps to a certain label that you specify. There's other J-type instructions that you can look into. Jump and link are used for function calls. We've also attached a PDF for your reference if you wanted to implement that in your program. So jump will go ahead and change the contents of the program counter and jump to that instruction. So putting it together, you're going to be using Mars, which is a MIPS assembler. You create an ASM and you can write your assembly code in there. They'll also do syntax checking for you and highlighting. But to put it into your FPGA project in Vivado, you'll go ahead and through the settings, settings, you will select memory configuration, and then you'll select the compact text at address 0 option. So this will put all your instructions starting from address 0. So when you load into ROM, when the program counter reads from there, it would read starting from address 0. From there, you go ahead and assemble your assembly code, and then go ahead and click on this option, which will generate hex code, hexadecimal text for you. And then I'll put that file, and you'll be placing this into your ram.mem. And there's a rom.mem file, so that would load it into the ROM. There's also a corresponding ram.mem file for you. It's all documented in the GitHub project. So as mentioned previously, if you want to learn more, you can learn more about functions and function calls. Okay. You can also implement arrays, while loops, for loops, and other higher level constructs. So that's all documented in this PDF. That's also available in the drive. And if any of you want to go ahead and pursue this, you can also ask us for help. And that concludes our MIPS demonstration. Does anyone have any questions? Any questions in the video call? Oh, as an instruction? Oh.
So you'll make it available? Is that what you're saying, Phil?
Okay.
Gotcha.
Got it. Okay, thank
Thank you.
you.